Imagine Krishnan, who lives right next to the sunny, sprawling beaches of coastal Chennai. One morning, after a heavy rainstorm, he wakes up shivering and decides it is exceptionally chilly outside. Now, if Krishnan called his friend Amir, who lives surrounded by the icy, snow-banked roads of mountainous Kashmir, Amir would likely find Krishnan's version of a chilly morning to be incredibly warm. The human body constantly adjusts to its local environment. What feels cold to one person feels pleasant to another. That makes our personal physical sensations completely subjective and unreliable for measuring what the atmosphere is actually doing. For centuries, humans recognized this flaw and tried to bypass their own senses by watching nature instead. They noticed frogs croaking loudly or ants rushing to move their eggs to higher ground just before a severe storm rolled in. These evolutionary behaviors are brilliant survival mechanisms. But observing an ant colony cannot tell a modern farmer exactly how many millimeters of rain will fall, nor can it give an airline pilot the exact wind speed required for a safe landing. To accurately predict the sky, we had to move past subjective feelings and animal instincts. We needed an objective, universal system to measure the air around us. That system starts by defining exactly what we are measuring. Weather is the state of the Earth's atmosphere at a very specific time and place. Looking at this diagram of the Earth's atmospheric layers, we can see exactly where that state changes. The lowest layer shown here, resting right against the land and ocean, is the troposphere. This is where humans live and where all weather actually takes place. It extends outward anywhere from 6 to 18 kilometers from the ground, capped by a distinct boundary line called the tropopause, which separates our weather-active layer from the calmer stratosphere above. Because the specific gases, heat, and moisture swirling inside this layer are mostly invisible to the naked eye, scientists had to invent specialized tools to translate these physical properties into hard, trackable numbers. The first of those physical properties is temperature, the exact measure of how hot or cold the surrounding atmosphere is. To capture this, meteorologists rely on thermometers to record the absolute maximum and minimum limits reached during a 24-hour cycle. By subtracting that daily minimum from the daily maximum, they find the range of temperature. This specific data point reveals how drastically the heat fluctuates in a given region over a single day. Once the heat is calculated, the next critical element is precipitation. This covers any form of water falling from the sky, whether that's rain, snow, sleet, or hail. To quantify this, scientists use a rain gauge. It's essentially a funnel that directs falling rainwater into a specialized cylinder, allowing observers to measure the exact depth of the accumulated water in millimeters. By combining a simple thermometer and a rain gauge, human subjectivity is removed from the equation. Physical heat and falling water become precise, universal data points that anyone can understand. While we can feel heat and see rain, the atmosphere also exerts a constant, invisible weight. This third element is atmospheric pressure, the physical force of the air pressing down on the Earth's surface. You can feel this weight change traveling to high-altitude mountain passes like Kardungla. Up there, at over 18,000 feet, the air is thin. The pressure drops, meaning there is less oxygen packed into every breath, forcing the human body to work harder just to keep moving. To measure this invisible weight down at sea level, scientists use the barometer. These instruments calculate the air's weight in units known as millibars. The standard pressure at the coast is around 1,013 millibars. If a barometer suddenly drops below 1,000 millibars, it signals that the local air weight has rapidly decreased. This creates a low-pressure depression, warning meteorologists that a severe storm or cyclone is likely forming. Tracking atmospheric pressure effectively gives humanity the ability to see violent weather systems long before the first drop of rain actually falls. When air rushes from an area of high pressure into one of those low-pressure depressions, it creates our fourth element, wind. Wind requires two distinct measurements. A simple wind vane determines the direction the air is moving, while an anemometer, which catches the breeze in rotating metal cups, measures the exact speed in kilometers per hour. Finally, we have the fifth element, humidity. This is the amount of invisible water vapor suspended within that moving air. We track this using tools called hygrometers, which measure relative humidity on a scale from 0 to 100%. This measurement explains why a coastal city at 80% humidity feels sweatier than a dry inland town at the exact same temperature. Wind and humidity act as the delivery mechanisms of the sky. They dictate how a weather system moves and how much moisture it carries as it approaches a population. An isolated thermometer, or a single barometer, doesn't give us the full picture. The true predictive power of meteorology only emerges when you monitor all 5 of these measurements simultaneously. This requirement led to the creation of the Automated Weather Station, or AWS. An AWS is a self-operating array of sensors. 24 hours a day, without any human intervention, it constantly gathers data on temperature, precipitation, pressure, wind, and humidity. By linking thousands of these stations together across the globe, isolated observations are transformed into a massive, continuous stream of numerical data that powers the computer models forecasting our weather. Which brings us back to Krishnan in coastal Chennai and Amir up in Kashmir. Today, they don't have to argue over whose morning feels more chilly. They can bypass their own senses entirely and simply pull up the precise, objective data generated by their local weather stations. By tracking temperature, precipitation, pressure, wind, and humidity, science has successfully broken the chaotic forces of the sky down into measurable numbers. We finally have a universal language to understand, respect, and survive the natural world above us.